Let's dive into the course, that is exploring LiDAR data with ArcGIS Pro. So LiDAR, which stands for light detection and ranging, which uses laser pulses to capture high resolution elevation data, and which has many applications in GIS. Okay, right from in various domains: urban planning, agriculture, forestry, etc. So this LiDAR data can be used accurately to represent the height and even the shape of any objects. For example, the buildings, the trees, the electrical poles, etc. So it can help determine when the stand of commercially even timbers are ready for harvest. So there are so many applications. So in this webinar, we will be exploring about how do we organize, process, visualize, and share the LiDAR data in ArcGIS Pro, and then how do we create mosaic data, and then we can also explore how to create various surfaces. All right. So there are a few modules in this. In the first module is exploring LiDAR data. So the main topics covered in this first module are LiDAR data collection, comparing LiDAR data formats, LiDAR classification standard, and exploring common LiDAR applications. So in the last decade, there is a huge expansion in the use of LiDAR data, especially in the GIS domain. The growth in the amount of available data and increasing this number of applications where it is captured have resulted the use of GIS professional to better understand the LiDAR data and how it can be used in various GIS contests. Okay, so so now what is LiDAR? So as I told you, LiDAR, light detection and ranging, is an optical remote sensing technique that uses laser light to densely sample the surface of the earth, and which produce high accurate X, Y, and Z measurements. That is, you have latitude value, longitude value, and the elevation value. So in this LiDAR data collection, the laser pulses are transmitted towards a target while moving through a specific route. So it has a track, whether it can be airborne data or even the terrestrial laser scanners. There is a track. And during the track, it will send the pulses. So the reflection of these laser from these targets is detected and analyzed by the receivers. So once it sends the laser pulses, it will also receive the back signals once it is hit by the objects, and once we receive it back. Okay, so these timings are combined with positional information of the sensors and then transformed to measurements of actual three-dimensional points of the reflective targets in the object space. So this is how the LiDAR remote sensing works. Okay, so here the LiDAR produces mass point cloud data sets that can be managed, visualized, analyzed, and sharing using ArcGIS. Right. So now let us see what is a hardware component of LiDAR system includes. It includes a collection vehicle, that is either the airplane, helicopter, or even automobile, and a tripod, and there should be a laser scanning system, and then GPS, which measures the locational information, and then there is INS, which is inertial navigation system, which measures the orientation such as roll, pitch, and heading and velocity of the LiDAR system using the gyroscopes and the accelerometers. Right. So this is what the LiDAR does. So and then now coming to LiDAR returns. LiDAR pulses emits from a LiDAR system, as I told you. So there is a sensor which will emit the pulses, and once it touches the objects, it will receive the returns, right? So there are so many objects that are present on the ground surface. For example, vegetation, as you can see in the figure, buildings, bridges, and so on. So once this emitted laser pulse can return to the LiDAR sensor as one or up to 5 returns. So sometimes the pulse, when it hits on the top of the tree or top of the building or on the ground surface, so the returns will go from that particular surface. So there will be multiple returns as well, or there will be even first return and even last return. So as you can see, the amplitude of the return and the time when it is reaching back to the sensors. On this figure, we can clearly see what is the first return, what is the amplitude it is giving, and so on. What is the last return? So any emitted laser pulse that encounter these multiple reflection surface as it travels towards the ground is split into many returns, and as there is reflective surface. So generally, the first return of any given laser pulse is normally associated with the top of the surface of the features. For example, building top, or even the tree top, or any other objects. For example, as we see electrical poles, bridges, etc. So the first return can also represent the ground, and if it is there is a open space, that time the playgrounds, the open areas. In that case, the first return may be the ground as well. So multiple returns are capable of detecting the elevations of several objects within the laser footprint of outgoing laser pulse. In general, the intermediate returns are used for vegetation surface or some other objects, and the last return is used for bare earth terrain models. So we will get the elevation of the bare earth surface and also the elevation of objects present on that ground surface. So now let us talk about quality of this data collection. Okay, so there are two major criteria that defines the LiDAR quality levels, that is QL. The first criteria is point density, measured as points per square meter, and the second criteria is vertical accuracy. Okay, so the USGS, that is US Geological Survey, defines QL1 as 8 points per square meter within a nominal point spacing at least 0.35 meters and a vertical accuracy of at least 10 centimeters. Okay, so this is defined by USGS. And then there are various products that are derived from the QL1 LiDAR, that is DEM at 50 centimeters resolution and 1 foot contour. And then of course detailed above ground feature mapping is also possible. If you want to highlight the transmission towers, building footprints, vegetation structures, sewers, culverts, and other man-made structure, any other infrastructure. So this table basically summarizes the quality of the LiDAR data. As you can see, there is QL0 to QL5. In QL0, we say it is the vertical accuracy is up to 5 centimeters, whereas the nominal pulse spacing is less than or equal to 0.3 meters, and the nominal pulse density points per square meter, which is more than or equal to 8 points per square meter. And the digital elevation model that we can generate out of it is 0.5 meters, and so on as we go to the higher number qualities, that is QL4, let us say, which is a data source which is from imagery, whereas the vertical accuracy is 139 centimeters, out of which we can only able to create a digital elevation model with a spatial resolution of 5 meters. All right, so one should be clear about their project objectives. which quality level data that is required to achieve the accuracies. And now coming to LiDAR attributes. So far we have seen LiDAR quality, and now once the data is acquired, the LiDAR data has lot of attributes, that is intensity, return numbers, number of returns, point classification, edge of flight line, RGB, GPS time, scan angle, and scan direction. So there are so many attributes. So one thing you need to remember, scan angle. So always you need to remember what is the scan angle of your data and the scan direction as well.
Dr. Varma, we have a question. What do we mean by vertical accuracy?
Yeah, we will take the questions at the end of the presentation after the hands-on demonstration as well. Okay. So intensity is basically the strength of the laser pulse that generates the LiDAR points, and the return numbers we have already discussed. There may be up to 5 returns, and the number of returns is a total number of returns for a given pulse, and then point classification. See here, every LiDAR point is post-processed and can have a classification that defines the object that has reflected the laser pulse. So these LiDAR points will be classified into several categories. That is either the bare earth, top of canopy, or water. Right? There are some numeric integer codes which does this point classification. So we will explore more about this in the hands-on session in ArcGIS Pro. And similarly, we have all other LiDAR attributes as well. Okay, so these are some questions. Once we understand this, we will be able to answer this. What are the attributes present in the LiDAR data that we are going to use? So once we explore it in ArcGIS Pro, you will be able to understand these properties of LiDAR data sets. And now comes the classification. Okay, so once we have these large data sets, usually given by the data provider, and there is American Society of Photogrammetry and Remote Sensing standard is there, which will classify the data into different classes. As you see in this figure, all this point cloud data is classified into almost 18 classes. 0 is never classified, 1 is unclassified, unassigned, 2 is ground, 3 is low vegetation, 4 is medium vegetation, 5 high vegetation, 6 we have buildings, noise, and then model key are reserved, 9 is water, 10 is rail, 11 is road surface, 12 is overlapped, and so on. Okay, so we have for each large data set, there are classification that is provided. And now collection of the LiDAR. There are several methods in which the data is collected. So the especially that is airborne data and terrestrial laser scanner. In airborne data, the sensors are mounted on the aircraft, and the pulses will be sent, and then LiDAR data collection will be carried on. And then in the mobile terrestrial LiDAR scanner, you can also mount your LiDAR system on any device, on any vehicle, and then you can collect the LiDAR data. So these are the some of the common collection systems of LiDAR data. And then now next comes to the storing of LiDAR data, right? So when we say storage, there are various formats. One is ASCII format, another one is LAS format. So in ASCII format, what happens? LiDAR data, initially it was delivered in ASCII text format. This format was easily supported by various software programs, and it is in so many other softwares also, not only in ArcGIS Pro. In many softwares, ASCII format will be easily opened. But when we have large amount of LiDAR data in single collection, frequently it results in massive file sizes. So it is very difficult to work with ASCII data if you have large volumes of data. Okay, so the LiDAR ASCII formats basically represents the LiDAR returns as a grid. As you can see, there are header file and then we have cell value heights, as you can see in this. So this is how the ASCII file is stored. It is also supported ArcGIS Pro format for LiDAR data, but it is primarily used for interchanging between different software systems. So now next comes the last data. So last data is industry standard format maintained by ASPRS, and then which maintains full metadata for LiDAR survey, that is flight date, time, and so on, and also all the attributes, right? It is published as a standard file format for interchange of LiDAR data that maintains specific information related to LiDAR data. So it's a way for various vendors and clients to interchange the data and maintain all the information specific to that last file. Okay, so make sure if you have a last file, you will be having X, Y, and Z location information, GPS timestamp, intensity, return numbers, number of returns, point classification values, scan angle, and there will be additional RGB values, scan direction, and then other information. So now let us explore all this in ArcGIS Pro software. So let me share my screen. Before we move on to the module 2, we will explore it in ArcGIS Pro, and we will open some last files and see all these properties that so far that we have explored. All right. So now let me share my screen. Just give me a moment. I hope all of you can see my screen, ArcGIS Pro, right? So now I will open some project which has LiDAR datasets. All right. So click on this open project. I already have some data with me. So I'll just go and open this project, LiDAR. Okay. So here, let me reset my panes first. So click on mapping. So in this project, there are a lot of data. Go to the folders, and inside this folder, as you can see, we have various large data sets that is already available, and then there is USGS last original data sets, that is their last files, and then there is classified files as well. Okay, so we will use some of these data sets in ArcGIS Pro to see to explore about last file properties and visualization options. So firstly, what I am going to do is I am going to load any one last file, and I will see how to load it and visualize this point cloud data. So let me load any of these last file. So I just simply drag it from the catalog window to the map. Okay. So now, as you can see, it is a point cloud. You can see there is points. So now we can zoom in and see, click on any of these point, and we can see the information related to this last data. So here what is written? Class code 3 written, 1 written, and then classification. And then GPS time, scan angle, scan direction. So all these information will be there for each and every point. Okay. So now just right click on this layer, go to the properties, and then we can see there are source, elevation. In the source, you will find what is the file name, extent, and then what is a spatial reference that is used here. Here, for the spatial reference used is PCS, that is Lambert conformal conic projection, North American datum for both the X and Y. And for vertical coordinate system, it is used NAVD88 geoid 03. So when you are working with LiDAR data, you will have this vertical coordinate system as well. But when you are working with XY data, mostly you will have only these two things: projected coordinate system and geographic coordinate system. Okay. And after this elevation, elevation tab, and then here in the properties, if you see, earlier we have discussed classification codes, correct? So there are so many classes. If you click on all the points will be displayed. If you click only for buildings, let us say just click on buildings, only you will be getting data for buildings. All right. After this, there is last filter from which you can apply all these classification codes, so that only the data that will be displayed for that particular classification codes. Now let me turn off this and then only click on buildings. Let us say just click apply and see, only for buildings the data is loaded. All right. So this is how you can apply filters on the last date. Okay. So now let me remove the filters. Go to properties. I will click on all and then click apply. Okay. So now see. So this is the complete footprint of the data. So now if I click on this footprint, it will give me the entire last file details. How many written values are there? What are the classification codes? What is jet range? Point spacing. Please remember this point spacing. Based on the point spacing, we will be generating the digital elevation models, whether it is DSM, DTM, or DHM. So we need to remember what is the point spacing. And then we have written values, and then classification codes, and then classification flags. Okay. So this is about last file and its properties. Now go to the catalog. In the catalog pane, on this last file and see these properties. So here you will have complete summary of this file, and then here if you go to statistics, so if you want to update the statistics, you can click update statistics. It will calculate again, and then you can see the attributes, returns, and classification flags. And here you have last filters and then coordinate systems. So these are the properties of last file. I hope this is clear to all of you. How do we load the data and explore its properties? Next, what we will do is we will create some 3D scene of this, and then we will load these data sets. Okay, if you go to last data layer, and there are various methods you can apply symbology for this data set. So just click on this elevation. Okay, let us say elevation. Based on the elevation, the uh, point cloud data is visualized. Now if I change it to let us say class. Okay, so all these point cloud will be classified. If you can see in the left hand side, all these points will have a different color code symbols. Okay, or if I choose any elevation surface, so it will just create one elevation surface out of this point cloud data. Okay, so you can apply any type of symbology to this large data set layer. So right now I am going to keep it as symbolize your layer using the points, that is elevation data. Okay, and if you want to keep on contours or edges also, you can do that. So now for the moment we will keep it for edges. Okay, so after this now I am going to create a new local scene and then insert. So I am just going to click on convert and then I will click on convert to local scene. See, after this is loaded into 3D scene, and then I'll just use these visualization techniques and then see the point cloud data. Okay, now just I will increase the ground elevation vertical exaggeration to 1.5 so that we can able to see the large data sets. So this is how you can visualize your data. If there are any outliers in the data, you can able to clearly see. So there are 2 points here. See, when the data is acquired from the airborne, so there might be some outliers in the data as well. Okay, so like this, you have to explore the data. So the height of these two particular points are actually very uneven. So this might be because the reflection may come from the birds or any other noise in the data. So you need to remove these outliers before converting any of these surfaces out of the LiDAR data sets. All right. So now I will move on to the next topic, that is creation of the LiDAR data sets. So just let me share my presentation again. So here we will be learning about how do we create large data sets, mosaic data, point cloud scene layers, and how do we work with large data sets. So far we have seen a last file, which is a quick process to display and do the data exploration and editing. And whereas for JEDLAS, what it does is it will compress and optimize the LAS files, which is mostly useful for archiving, sharing, and direct use. And also, it is only the read-only format. So always remember, JEDLAS is read-only format. So it gives a uh, source to the your original LAS files. And then now coming to the large data sets. So the main advantage of large data set is it will try to manage multiple LAS files as one single data set. It can be used in 3D analysis. It will help also in quality assessment and quality control. The classification can also be edited in this last data set. So what we need to do is we need to convert our last files into last data sets. And then next is mosaic data. So mosaic data, there are so many formats that we can generate from the large data sets, that is digital surface model, digital terrain model, digital height model, or you can generate hill shade, right? So many surfaces that you can generate out of these large data set. So what we can do is we can mosaic all these and we can create a mosaic data sets which manages LiDAR as a raster outputs, and these mosaic data can be used in this raster analysis and various other functions. And the last one is point cloud scene layer. So this is one of the this is one of the fastest way for display, and it can be shared as a web layer or a package file. So now let us understand what is a large data set. I hope I am audible to all the participants. Okay. If anybody is not able to hear, please check your audio jack. So now let us understand what is a large data set. A large data set basically it refers to access and one or more large files. So basically it is just creating one grid in which it will reference all the large files. Whenever you zoom in, that particular large file will be loaded and it will be helpful for display in both 2D and 3D environment. And of course, when we are loading these data sets, there are various constraints which we can apply, such as surface constraints, and there are editable constraints. So now let us say there is a water body, or for example, there is a playground. So in the playground, when I am going to create these large data set, I will specify some constraints. I will say for all these, for this entire location, the elevation value is uniform. Okay. So this is how I will specify some of the constraints. Or for example, I wanted to only load to my area of interest. You may have collected the LiDAR data for a larger area, but however, there may be some administrative boundaries that you wanted to work inside only your area of interest. So in this figure, you can clearly see on the right hand side, whereas constraint applied. So what it has done, it has clipped the original data into a specified area of interest. So these are called surface constraints. So here there is one type of constraint is applied. So there are different methods, constraints are there. So we will learn about how to explore these large data sets, work with large file connections as one seamless data set, and we will filter the written points of all the input large files at once and visualize the thin surface from it. Okay. So now let me share back my ArcGIS Pro software again. We will explore now how to create large data sets out of it. I hope my screen is visible to all the participants. So just I'm going to click on view tab, click on geoprocessing pane. See, in geoprocessing pane, there are various tools here. So here in 3D analyst, you will have some point cloud tools, right? So there are various other tools where you can convert all your large data sets. Okay, so in the data management tools as well, you have large data set. So in this large data set, you can create all your large data set statistics and then add files to large data set and so on. So now let us add some last files and create a last data set. So we have a geo database, that is lidar.geo database, and then there are various files that are given to us, that is stream files and steady area vector files that is given to us. Okay, so now let us first add these files into our map. So go to the catalog pane and then go inside this geo database. Inside this geo database, we have steady area and then state college streams. So let us add all these files into the map. Okay, so now let me turn off this. Oh, I'll just zoom into this layer. See, this is my steady area. Okay, so and then I have there are some streams. Okay, so there is a stream network. So when I am loading the data set, I will be keeping this as a constraint. Okay, so before creating the steady area, so let me keep this in mind. So when I am going to create this last data set, I have to honor these constraints which we have discussed in the presentation. Okay. So now let us create large data set. So browse to the data where there is files that are given to us. And then we will go to create large data set tool. So there is a tool called large data set tool. So before this, the data is located here in US State College. There are so many large files. So create large data set. Okay, so that tool is located in data management. All right, last data set. So inside this, click on this tool, go provide your input last files, go to the folder connection, and then inside this LiDAR, you have various last files. Okay, so now let me add these three files. Let us say open, and then output last data set. I will keep it as it is. Now it is asking for the surface constraints. So as I told you, steady area and streams college. So I can give it as input features. Steady area, I will give it as soft clip. So input feature steady area, provide it as a soft clip, and then click on streams. And then here it is a hard line. Okay, coordinate system automatically it will take it from your input last file that is already that is added in the contents pane. Okay, after this you can click on compute statistics button, and then we can just click OK. So what will happen, it will create one last data set, right? So earlier it was only one data set, now it is completely created for three different class files. Okay, same way we can visualize these points in 3D scene as well. So after this, now let us say if I want to add a few more files to this particular last data set, so you can go explore the properties. You can see what are the surface constraints added here, and then you can see the metadata source as well. After this, go to the catalog and see where this is stored. Last data set. D-leader. It is provided in the folder D-leader last data sets. Okay, just click on refresh. So here the last data set file is stored. Okay. So now let us say I wanted to add few more files to it. So what I need to do is I need to go to the properties of it, and then last files tab will be there. On that last files tab, we will be adding few more files to it. Go to the properties, click on last files. And if you want to add a few more files to it, let us click on add files and then go to the folder connections and then go to USGS State College last classified. Now let us add few more files to it. Okay. And then now we just need to compute the statistics for it. Okay. So now still now this data set is not visible. So because we have not computed the statistics for it. So just go to this data and then click on compute last statistics. Okay, just click on run button. So now the data is loaded. So you can zoom in and then we can clearly see this point cloud data. All right. So this is how you will be creating the last data set. And then now let us see, as I told you, there are some outlier files. If you want to explore it, we need to explore right from a 3D data. So just open the 3D file, that is scene, go to maps, QA/QC. So let me load this. And then just add the layer that we have just created. Okay, just drag it and drop here and then click OK. So now just zoom out where there is see, as I told you, there are some outliers in the data sets. So once you load it in the 3D environment, you will be able to see all these uneven heights. So there are some data sets which are at same level, but there is one particular last file which has so many outliers in the data sets. All right. So now let us proceed to next module, that we will try to create some surfaces, that is digital terrain and digital models. So let me share back. So share back my presentation. So this will be the last module. This may take a few more minutes. So in the third module, what we are going to learn about creating surfaces from the large data sets. So the surfaces such as digital terrain model, which is a bare earth surface that is created mostly using the ground hits. And then there is another one, that is digital surface model, which will be created with the highest returns, which includes the ground, trees, and other objects such as buildings, electrical poles such as. After this, there are various tools which will try to convert the last data to raster tool with along the constraints that we have loaded, and which will convert your point data to raster image. Okay. And of course, you need to follow certain parameters when we are generating the surface, because based on the sampling points, the surface will be created. And of course, there are triangulation, binning, so many parameters are there in which you will be computing your surfaces. So now let us explore how to create these DSM, DTM, and DH, which is main outputs of LiDAR data. Let me share back my ArcGIS Pro. I hope ArcGIS Pro is visible. So now again, what I'm going to do is I will be first to the last filter tab, and then I will create one digital terrain model. So for creating it, I need to only filter the data that is ground box. Okay, so just go to the last filter file. So click on this, go to the last filter file. properties, go to last filters and remove all this and then only keep ground. So this way I can generate a surface out of it. So on the bottom, if you want to keep a satellite image, you can keep a satellite image. Otherwise, if you want to keep a topographic map, so now it is simple to generate all these DTMs. So you just need to go to the data tab, and from the data tab, we can click on export raster. So just go to the data tab, and then here export raster option is there. So now what we are going to do, generating surface out of this point cloud data. So output raster, by default, I am leaving it as it is. So I just rename it as DSM. Okay, so the value field will be remain elevation, and then interpolation type triangulation, and then linear, no thinning, and then cell size, which we need to give it as 15, because as I told you, the based on the spacing, we need to specify it. Ideally, the thumb rule is 3 times the point spacing. So the resolution in which you need to generate your digital surface model is 3 times the point spacing. For me, it is 5 feet. So I have given the sampling value as 15 feet. So now let us see the DSM is generated. So now let us apply some symbology to it. Just right click on the layer, zoom to layer. And as I told you, the constant is applied. So the entire last data file is clipped to our steady area. And now go to the symbology pane. And we will change the color scheme here. And then go to more color schemes, click on elevation. So just click on elevation 1. So this is the bare earth model, which is not having elevations of any other objects that is present on the earth surface. Now what we can do is we can provide a DSM. So for doing this, what we need to do is we need to change the classification codes similar to this, but only we will remove one particular class file, that is class number 12. Okay, we will check all the points, but we will remove the class number 12. And again, we will repeat the same process. We will click on export raster. This time I will give it as surface model. Sorry, earlier I have written terrain model. Okay. So this is DSM 1. And then binning, here again triangulation method only we will take it, and then linear, no thinning. Floating point cell size we will keep it as 15, and then we will click run. Okay, so it will generate my terrain model and surface model. This may take a little time. Yeah, so now we have got the elevation with all the objects, buildings and other objects. Now let us go to the symbology and then change the color scheme to elevation. So just type elevation. So after this, if you want to generate any hill shade, so you can generate hill shade. So go to the imagery tab, raster functions, click on shaded relief. So provide your DSM, and then here color ramp, you can give it as it is. You can keep multi-directional, and then you can create a new layer. So this is the shaded reliefs. So now what I am going to do is I am going to keep my elevation model on top of this shaded relief, and then I can apply the enhance the visualization with the layer blend option. So I can click on multi. Okay, so this is how we can apply the change the visualization of this terrain model. After this, there is one model which you can generate, that is NDSM or DHM, digital height model. If you only want the height of the buildings or the trees, or even if you are working with forestry, the correct terminology is called canopy height model. So what you need to do is you just need to subtract these two files. Okay, one we have bare earth elevation model, another one which we have along with all the objects. So in the uh, data management tools math, so just type minus. Yeah, so just double click here. In the spatial analyst, in the math, you can find these two tools. So what you can do is you can just give subtract one elevation value out of another, so you will get the height of the buildings. Simple. Okay, so it is DHM. This, if you want to visualize the height of this in any 3D, you can load it in 3D as well. Okay, so so now we have got elevation of each and every building. We can just click on this and we can see the stretched pixel value and on the ground. Okay, if you go to any bookmarks, so let us go to campus research area. So we can see clearly the height of the buildings. Okay, so this is it. This is how you can process the LiDAR data and generate the surfaces. Now let me share back my presentation. So I thank you all for attending the webinar.